Alright, so for some reason my video kind of stopped working there for a second. So we were talking about coming up with the line of good fit. We had gotten to the part where we were filling out these errors, and hopefully you got these error values. And remember, we were taking the observed value minus the predicted value to get the error. Then what we want to do is square all those errors to make them all positive, and then we're going to find the sum of the squares of those errors. So we're going to add all of those errors up, add all of those squares of the errors up to get this value right here. And basically the idea here is that the smaller this value is, the better. And that the line of best fit will be the one with the smallest sum of the squares of the errors. Just a visual representation of this is, here we have all of our residuals are represented by dotted lines. It's the distance between the predicted value and the observed value. So I put these dotted lines in there. And then what we're doing is we're squaring those values. So we're going to build these squares, and you might be thinking, hey, I remember this from when we did standard deviation. We found the distance between the values and the mean, and then we added them all up, and we found basically the average square to find the variance. And we actually did something just like this with standard deviation. So here are all of our squares. So we're basically taking the areas of these squares and adding them all up, because we know area is a positive value. We have negative values right here, so we're going to make all of those values positive by squaring them, and then we can take all of these areas and add them all up to get the sum. And the smaller your sum, the better the line. So hopefully somebody was able to get a better sum of the squares than mine was. But that's basically how a line of best fit works. For the next part, how do we find the line of best fit? Well, we're going to use our calculator for that. You're going to hit the stat key, go to edit, you're going to put your x's into L1, your y's into L2. You'll hit stat calc number 4, which is the linear regression. The linear regression model is the line of best fit. It's not a line of good fit. You do line of good fit by hand. The line of best fit is your linear regression model. Alright, so let's work on a couple of problems from the lesson master. The first problem, why is the process of finding the line of best fit sometimes called the method of least squares? And that's because the line of best fit will give the least value for the sum of the squares of the errors. So the smaller the sum of the squares of the errors, the better. I'd like you to try number 2 using sigma notation to write an expression for the center of gravity of the data set, and then hit the pause key to check your answer. Alright, so in this one, hopefully you got that we're finding the average x and the average y. So we're adding up all of the x's from 1 to n and dividing by n, and we're adding up all the y's and dividing by n. You could have had 1 over n times the sum of all of these, and 1 over n times the sum of all the y's here. But either way is fine. Number 3. Try number 3 and 4. I'd like you to read that carefully and try and see what you get. Alright, for number 3, the first thing you want to do is know that, okay, M1 and M2, M1 is the linear regression model, so this is the line of best fit. It's not going to get any better. Line M2 represents some other linear model, one we came up with by hand for example. So the sum of the squares of the deviations for M1 is going to be less than the sum of the squares of the deviations for M2, because line M1 is the absolute smallest sum of the squares of the errors that we can get. So it better be the smallest, it better be less than the sum of the squares of the deviations for M2. If every point lies on M1, then the sum of the squares of the deviations for this model is, if there are no deviations, if every data point lies on the line, then there won't be any deviations, which means that I'll be taking a whole bunch of zeros, squaring a bunch of zeros, adding a whole bunch of zeros up, and you're going to get 0. Alright, for number 5. Alright, we have the breaking strength data for polypropylene rope. Use the statistics utility to find an equation for the line of best fit for this model. Okay, you guys can do that. Remember, these are going to go into L1, 5, 6, 8, 10, 11. And L2, you're going to put 7, 80, 11, 25, 1,710, etc., 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 and come up with the line of best fit. Okay, hopefully you were able to get something like this. They rounded to the nearest tenth, so we'll have y is approximately 501.7x minus 2,153.2. And then we're going to use that model to find the error in the values predicted by the linear regression model from the breaking strength of ropes with diameters of 12 millimeters and 18 millimeters. So if we're finding the error, we know that 12 millimeters, the breaking strength is this much, so we need to use the model to come up with a prediction for the breaking strength of 12 millimeters. And then we're going to subtract the observed minus the predicted. And you're going to do that for 12 and for 18 millimeters. So find the y values. If I put 12 in for x, find out what the y values would be, and then subtract the observed minus the predicted. Alright, you should have got negative 87.2 pounds for 12 millimeters. And for 18 millimeters, you should have gotten 772.6 pounds. In letter C, use the equation you wrote in part A to estimate the breaking strength of ropes with diameters of 13 and 25. This one's actually easier than part B. All you're doing is putting the 13 in for x and putting the 25 in for x. So, go ahead and do that, and when you're ready, hit the play key. Alright, hopefully you got 4,370 pounds for 13 millimeters and 10,389 pounds for 25 millimeters. And then it asks you which estimate do you think is more accurate and why. Well, the 13 millimeters, that's right between 12 and 14, and that's inside of the range of our data set. So this is an example of interpolation. The 25 is 7 units away from our highest estimate, so that's going to be extrapolation. So because the 13 millimeter estimate is inside of our data set, we're going to have we can make a better prediction based on the data that we have. But since we don't have a whole bunch of, we're going to have a whole bunch of missing data over here. So making a prediction for 25 millimeter strength, or the strength of a 25 millimeter rope, I don't think that would be a very good prediction compared to that of the 13 millimeter estimate. Alright, on the back, we have these 4 points, and we have a student who fit a line L to the data points, and it's shown below. And right now you can just ignore these green lines, and we'll come back and talk about those. What is the observed value of y at x equals 4? Okay, so the observed value is important. Observed means the data point. Okay, so when x equals 4, y equals 6. Okay, so the predicted value of y at x equals 3. Predicted means use the line of best fit. So we're going to go to x equals 3, go up to the line, and you should get 5 for that one. Estimate the error of each of the 4 points from line L. Okay. Go ahead and do that. We're doing each of the points from line L. What's the distance? What's the difference between those points and the data, and the line of best fit? Alright, for 2-6, you should have gotten an error of 3/10. For 4-6, you should have gotten an error of about 1.75. For 5-5, you should have gotten an error of about 1.5. And for 8-1, you should have gotten an error of about negative 0.4. Or if you said negative 0.5, that's obviously okay. And then we're going to find the sum of the squares of the deviations from the 4 points. So you're going to square all of those, all of these values up. You're going to square the 0.3, the 1.75, and then add them together. And when you do that, you should get about 5.39. So again, this is the sum of the squares of the deviations. Find the deviations, square them, add them all up. Alright. For number 7, using a statistics utility, the student found that an equation of the line of best fit is negative 88/100 x plus 8.68. So we're going to graph the 4 points and the line of best fit. Okay, so that was pretty much done right here. Okay, so if you need help with graphing a line, you can, I don't know, go back to Algebra 1. So here's our line of best fit, and here are our 4 data points. So to find the sum of the squares of the deviations, alright, find the deviations, square them, add them all up to get letter B. Alright, you should get about 2.48. Verify that the center of gravity is on this line. Okay, the center of gravity is the average x coordinate and the average y coordinate. Okay, well, the center of gravity, when we do that, you're going to get 19/4 and 18/4. Average x, average y. And to verify that this is on the line of best fit, we need to take 19/4, plug it in for x, and make sure that we get 18/4 out for y. So when we plug 19/4 in for x, multiply by negative 88/100 and add 8.68 or 8 68/100, we get 18/4. So this does work. It satisfies the equation, so it's on the line. So the center of gravity is on the line of best fit. And then how do we know that this is a better model, or how do I know that this line is better than line L? Well, it all has to do with what we got for part B. The sum of the squares of the deviations was 2.48. We got them by adding up the areas of each of these squares. Now compare that to the areas of these squares. You can see how these squares are a lot bigger than these squares are. So when I add those areas up, I got 2.48, and when I added these areas up, I got, what did we get, 5.39. So since the areas of these when added up was less than the areas of these green squares, then this is going to be a better model. So since the sum of the squares of the deviations is less than for line L, this is a better model. Okay, so that's going to do it for section 2.5.